So, good morning to all of you. So today we will have the fifth webinar from CITAC dedicated to presentations from the winners of the best CITAC paper 2024. So let's start this event with a welcome from the CITAC chair, Zoltan Mester. Please.
Thank you very much, Ricardo. If you would stop sharing, yeah, thank you. I have a few brief slides. So you should have my screen, I believe. So I would like to welcome all of you to the 2025 celebration of CITAC Best Paper Award. CITAC is a global organization with the aim to improve traceability of the results of chemical measurements everywhere in the world, and to ensure that analytical measurements made in different places and different times are comparable. CITAC is the oldest organization in the field of chemical metrology. Our primary outputs include guidance papers and guidance documents, usually developed in collaboration with EURACHEM and/or IUPAC. Our latest recommendation and report and guidance document was provided under the capable leadership of our past chair, Elia Kasselman, in collaboration with IUPAC on interlaboratory comparison of categorical characteristic of substance, material, or object, which was published as an IUPAC technical report also. So we produce guidance documents. We publish an annual newsletter, which is the go-to document for in-depth review and of progress in the field of chemical measurement science. So please look out for the 2024 report. It would be coming out in a few weeks. And we hold workshops, seminars, the latest one being the highly attended workshop held with EURACHEM on qualitative reference materials. I would like to flag for you the updated website. Actually, not the website updated, but our address has changed. Our new web address is citac.group. Please do not use citac.cc, our old address, anymore. It would lead you to non-CITAC related content. And last but not least, our key output is the award for chemical metrologists. This is a paper-based award premiating the best published papers in the field of chemical metrology or metrology in chemistry in the previous year. CITAC have been running this award program since 2007. Over this close to 20 years, we awarded 46 papers in total, close to 300 authors, 30 countries, and 5 continents. This is the premier award in the field of metrology in chemistry. So the 2025 winners are team from Inmetro Brazil in a very interesting paper dealing with QNMR based development of purity standards based on quantitative NMR, a truly independent set of describing a truly independent set of standards underpinning, organic analytical calibration infrastructure. And we are delighted to have Bruno Garrido presenting on this important study. The second awarded team and paper represented here by Giancarlo D'Agostino is an EU-based team from a Euramet project dealing with critical technology, critical elements, method development for the determination of technology critical elements in printed circuit waste. And the third one is an academic team comprising scientists from universities in Italy and Spain, represented today by the first author, Barbara Giussani, navigating the complexity, managing multivariate error and uncertainties in spectroscopic data and modeling. So congratulations to the winners. So here we are today having a live award presentation. The presentations are or will be recorded and posted along with the last 5 years of CITAC award lectures on YouTube. And I just would like to remind you that the nomination for the 2025 Best Paper Awards will be closing at the end of the year. So please consider nominating and celebrating the achievements of your team and colleagues. So thank you very much, and I am very much looking forward to the presentation today. And again, congratulations to the winners. Thank you. Ricardo, back to you.
Okay, let me show you a few slides about the awarding procedure, so you know a little bit about how it is done. Okay, can you see full screen mode? Okay, like Zoltan already mentioned, so this is one of the most important activities from CITAC, I would say, this awarding process, as he mentioned. So we have awarded already 49 papers, 299 authors from 28 countries and 5 continents. And we have a procedure that must be applied in the awarding process, and the criteria for awarding are the reference and developments on metrology and chemistry and biology published in peer-reviewed journals that the members consider relevant to disseminate good meteorological practices. So papers are nominated by CITAC members together with a nomination letter where they have to explain why they nominate the paper, highlighting the relevance of the research for meteorology in chemistry and or biology. And then the nominations are voted by CITAC members, and the 3 most voted papers are awarded, and there is no hierarchy of the awarded papers. So they have all 3 the first position, are all 3 equal winners. You can check the awarding procedure in the CITAC website. So this is wrong address there. So it should be citac.group there. And like Zoltan mentioned, so we'll have the chance to have the winners presenting their work, and we'll have also some time for discussion. So the first paper will be introduced by Zoltan. Zoltan already done that, but if you want, I can give you 10 more seconds to introduce the first presentation. Zoltan, again, if you wish.
Thank you, Ricardo. Thank you very much. Let me just turn on my computer. So the first awarded paper is by a team from Metro Brazil, by the authors of Wagner Wollinger, Jane Fernandez, Eliane Rego, Francisco Neto, and our presenter and last author, Bruno Garrido. Who I'm happy to say that is actually now my colleague at NRC, National Research Council, Canada. So this paper is dealing with the development of an independent, truly independent set of uh, of 8 reference materials underpinning organic calibration infrastructure for determination of organic high purity materials. There is only a handful of these exist in the world, so both the process and the fact that these materials are available are a major contribution to traceability of organic measurements. So without further ado, Bruno, the floor is yours.
Okay, thank you, Zoltan. So I'm going to start sharing my screen, and please let me know if there are any problems with my audio or my screen sharing. Uh, I'm actually in a travel right now, so I'm not using a very stable structure here. So hopefully everything's going to be smooth. Um, can you see the screen already?
Yeah, we have your screen, a full screen, so it looks good. So please go
Okay,
ahead, Bruno.
thank you. So, yeah, I would like to start by acknowledging and uh, thanking actually CITAC for the nomination, the award. We were very honored, and I should say also maybe a little surprised with the prize and the nomination, but we were very happy as well because we really think this is a very relevant work that we did. Uh, as you're gonna see, it's not uh, uh, fundamental paper on QNMR or on fancy pulse sequences, but we do believe that is a very relevant work in establishing traceability chain for QNMR measurements. So this is the title of the paper. It was published in Analytical and Bioanalytical Chemistry in 2024. Uh, and I'm going to start by showing actually the team involved in here. This was part of the PhD thesis of Wagner, who I supervised as his PhD supervisor. So this was one chapter, if you will, of his PhD work. And it actually started because his PhD work was going to deal with a lot of QNMR measurements. And as Zoltan mentioned earlier here today, there is a lack of traceable reference materials for use as QNMR standards in the world. There are a few available, but they might not be as comprehensive as we would like. So because Wagner had to do several QNMR measurements in his PhD thesis, we decided to actually start by certifying those reference materials. And so I'm actually going to start by taking a step back and talking a little bit about why high accuracy QNMR is important and what we've been doing to improve QNMR measurements. So a long time ago, or not that long, but probably 12, 13 years ago, we had this question within chemical metrology. Uh, is it possible to achieve 0.1% measurement uncertainty on QNMR measurements? And the first comparison that I'm showing here was done in 2012 for Aldrin purity. And here you can see that we had back then 0.5 to 1% measurement uncertainties on QNMR measurements done by different participants with a 0.6% RSD between all participants. And then in 2018, I'm showing here the bisphenol A purity comparison where we achieved a 0.1% RSD between participants with individual uncertainties in the range of 0.1 to 0.6%. So we actually improved. This is just to show that globally, QNMR measurements improved a lot in this period, and so it actually got 5 times better. And how did we improve so much? Then is the question. So one of the reasons why we improved so much is that we started a global BIPM and several NMIs initiative to improve and standardize QNMR. And this resulted in a series of recommendations on how to perform accurate QNMR measurements, which are the BIPM calls the QNMR internal standard reference data. So there are several of these documents, the QNMR standard reference data available at the BIPM website. And we've participated in drafting several of those. And then we published with the BIPM one paper where we went through a lot of different substances that would be appropriate to be used as QNMR internal standards. And then we assessed those substances in several applications, and we demonstrated that those substances were actually fit for purpose for doing QNMR measurements. So these were 7 different substances that we worked on with the BIPM. And based on these 7 substances, we then selected 4 of them to develop as primary CRMs in Metro. And as Zoltan mentioned already, independence here was a keyword because there are several CRMs available in the world that can be used as reference materials for QNMR measurements. But the problem with those reference materials is that they were certified by QNMR measurements. So they are all dependent on a common reference, which is normally a benzoic acid reference material. So it's all tied to, in terms of traceability chain, it's all tied to one. It's not all, I should say, but most of the reference materials available are tied to one single primary reference. So we actually wanted to have those primary CRMs. So the idea here was that we would not assign values for these reference materials using QNMR. Of course, we did a lot of QNMR measurements on them, but their certified property values come from a combination of a whole set of different techniques. So this is just for the records, I would say. It's just a description of why QNMR is a primary ratio method of measurement. So I'm not going to spend any time here, but I think this is pretty clear now in the metrology community that QNMR is primary ratio method, and it is really, really useful because it allows us to advance in measurements in fields where standards were not previously available, because QNMR gives us the capacity to go from a one-to-one calibration system where we need a standard of the same compound in organic chemistry. That's the case for most measurements. While in QNMR we can use calibrants that is a completely different structure, because QNMR is measuring nuclei and not specific structures. So there are no response vectors involved. And then we go from a one-to-one to a one-to-many calibration system, where we can use one reference material to calibrate many other different compounds. So starting with the reference materials that were developed, dimethyl terephthalate was one of the first, was the first actually reference material that we worked on. So here I'm just showing a little bit of the homogeneity data on this material, and it is important to highlight that all of the reference materials that we chose, all of the compounds that we purchased to do this development, they were extremely pure. So they were all well above 99.9%, if I'm not mistaken, but the values are going to be in the next few slides. And that means that in terms of homogeneity, for instance, we don't expect to see a lot of variability because we're dealing with extremely pure compounds. So we tried to do to use two different methods here. The first one was just directly measuring area ratios in HPLC with UV detection, but then the repeatability of the method was actually not good enough to deal with such a high purity material, and we would end up overestimating the uncertainties. So we decided to go with what we call a partial mass fraction or partial mass balance, I would say, where we actually determine the purity by measuring impurities. And the reason we call this partial is because we are not measuring all of the impurities, as it's just used for homogeneity assessment. And then we get much better uncertainties for the homogeneity determination of these materials, because that is one of the goals of the work was we should have independent materials, but their uncertainties also have to be small enough that they're still useful as primary standards. So this is what we got for all of the materials in terms of uncertainties for homogeneity. As I said, we ended up using the partial mass balance approach for the dimethyl terephthalate, which resulted in a much smaller uncertainty, but we didn't see any evidence of heterogeneity for any of the materials at all. And then we studied, of course, transport stability for all of them. There are no trends, there are no issues with this. So very clearly, as I said, we can see that those materials are pretty stable. We studied all of them for 50 degrees because we're in Brazil. That's our normal transport stability temperatures for study, and they are stable at 50 degrees for 60 days, which of course is not expected as a transportation time, but we still wanted to have more information on how long they would be stable at this time. And then this is just a little bit of our uncertainty budgets for the transport stability. Then the same issue we had initially for homogeneity assessments, we also faced when we tried to do our storage stability. Because there, for storage stability, we need to run analysis that are not necessarily in repeatability conditions. So the intermediate precision of the method starts to play a big role here. And then when we did this by using QNMR, which was the obvious choice, we saw that the uncertainties were too big. So we ended up applying also the partial mass balance here once again for the storage. And with that, those were some of our final budgets for the mass balance approach. We analyzed water, residual solvents, inorganics, and then the organic components by area normalization using HPLC with UV detection. One interesting thing that we did here was for residual solvents, we detected a little bit of acetic acid in the dimethyl terephthalate sample. And the only method that we could actually use to quantitate the acetic acid in that sample was QNMR. So just to show again that as long as we try to be, even though we try to be as independent from QNMR as possible, we still end up in situations where QNMR is simply the best measurement technique for some of our applications. And for measuring acetic acid is definitely one of the best things we could do. So we measured 0.005% acetic acid content in a pure sample by QNR, which is pretty impressive, I would say. And as I said, all of the purities are greater than 99.9%. So these materials are really high purity, and the uncertainties there are all below 0.1%. So they're all very fit for purpose for what we are doing. Then we, we wanted the independent reference values, so they were all assigned by mass balance, but we still ran them all by QNMR just as an orthogonal approach for comparison. And where possible, we also did colorimetric titration, which was the case for the KHP, for the potassium hydrogen phthalate. And we also did DSC, so freezing point depression, which is another primary method for both dimethyl sulfone and the dimethyl terephthalate as well, just for checking. But all the reference values, the assigned values for these materials were the ones from mass balance. Then again, this is just our uncertainty budget for the value assignment, and the final uncertainty budgets. They show the relative uncertainties for each component here. So I would like to use my last few minutes here to talk a little bit about the impact of this work and other activities, because as I said, the work itself is very important. It's very nice, but I think the impact of it in other activities is even greater, because we now have a proper traceability chain for QNMR measurements, and how this has impacted or is still impacting other activities in the field. So these reference materials are approved and are in full compliance with Inmetro's quality systems. Inmetro has CMC coverage for these materials in the KCDB, so they are fully compliant and fully usable by NMIs or any other users, really. And some examples of CRMs that were of the use actually of the CRMs produced in this study as internal standards for QNMR includes several forensic components, which I'll talk a little bit more about, and several CCQM comparisons. I'll also talk a little bit about one of them, and then some other measurements. But this just to show a list of reference materials that Inmetro has developed since the availability of of this QNMR internal standards, and for which this QNMR internal standards were used as the sources of traceability. So in terms of CCQM key comparisons, as I said, we recently had the oxytetracycline purity study, and maleic acid was used here as the internal standard for QNMR measurements in this comparison. Inmetro's results were perfectly right in the middle on spot with the key comparison reference value. So this is one example of the application of this reference materials as traceability sources for high accuracy measurements. And in this case, similarly to the acetic acid, which was quantitated by QNMR, also in this case, we detected acetonitrile in the sample as a residual solvent. And we couldn't quantitate it by Headspace GCMS, but we could quantitate it by QNMR. So again, quantifying trace solvents using QNMR and traceability with these reference materials. And just to highlight that Inmetro in this comparison, the CCQM K148B was not the only NMI that used these serums for QNMR. So just to mention also that the traceability provided by these reference materials goes beyond only Inmetro, but actually contributing to other metrology institutes in the world. Another field that Metro has been very active in is to provide traceability and forensic analysis, because that was a real issue in forensic labs in Brazil, because as we all know, importing drug materials can be really, really hard, and that results in a lack of traceability for forensic analysis, which can void entire criminal processes. So we started a program for development of CRMs in partnership with the federal police, and all the produced CRMs were characterized by QNMR using these internal standards. So that is also one very interesting outcome of this project. So some, not all, but some of the reference materials produced in this project, which include methamphetamine, caffeine, MDA, MDMA, MDEA, THC, CBN, cannabis, vegetable material. Several of these materials were synthesized, purified, and then certified by QNMR using the reference materials here. Also, several rounds of proficiency testing schemes were coordinated for the forensic labs, and they were all reference values assigned by using QNMR with those materials as well. We also produced a guide to obtain SI traceable results using QNMR written in Portuguese, because we wanted to actually make that technique more accessible for Brazilian users and other Portuguese-speaking countries. This is available online, and it's free of charge, just for download for anyone who's interested in getting traceable and accurate measurements in QNMR. As I said, the collaboration with the BIPM is still ongoing. Wagner has just recently published one of those internal standard reference data using fluorine QNMR. I worked on several others at the beginning of the project, so there are lots of materials there available. And just a little bit of other NMR research that was done in Metro. So as another part of Wagner's thesis, we also developed a high accuracy carbon-13 NMR acquisition scheme. And then we also have done more research like projects exploring correlations between mass spectrometry and NMR, and also time domain NMR, which was a very active area recently. So just to finalize, I wanted to thank you all again for the nomination, for your votes, and for stating that this work has had an impact and has been important for traceability worldwide. The QR code here takes you to the paper if you want to read it. And thank you all for watching the presentation as well. And I'm ready to take on any questions if you have.
Thank you very much, Bruno. The conference is open for questions or comments. Please just unmute yourself and speak up. Maybe I would start, Bruno. Seeing the development of these independent developments of these high purity materials for NMR calibration, are there any plans to cross calibrate or cross compare these materials via NMR or some other methodologies to see global consistency in this field?
Yes, thank you, Zoltan, for the question. We've cross-validated, if we will, these reference materials against each other. That's how we did the QNMR measurements that I showed in the project. But yes, we've also compared them to. So there's one other primary reference material that many labs are using. It is a NIST benzoic acid reference material. We've also measured these materials using the NIST benzoic acid. They're all consistent. So yeah, that's a good news in terms of traceability. But yeah, they're all internally consistent.
Thank you.
We haven't
Thank you.
compared them with any of the Japanese reference materials, though. The other nice set that I know of is from NMI Japan. We haven't compared them.
Maybe that's an opportunity for the Organic Analytica Working Group at CCQM to consider a CRM comparison on these high purity, NMR internal standards. Yeah. Thank you. Any other questions or comments?
Zoltan?
Yeah, Angelique, please.
Bruno, thank you very much for the presentation. It is very good also to have some more information on how you tackled this project. I just wanted to ask if there's something similar in the plans for carbon-13 NMR to also start developing suites of internal standards?
Yeah, thanks, Angelique. In terms of carbon-13 NMR, the measurements themselves are complex because we have to take into account the isotope ratio of the carbon present in the substances. And we've done this for some of these materials. So we've measured the site-specific carbon-13 isotope ratios for these materials and applied them to some carbon-13 measurements in another work. And that's why we developed the high accuracy carbon-13 sequences that I've shown. That is published as well. We applied it to nitrofuran metabolites where we didn't have any quantifiable hydrogens. But it is very complicated and you need to know the isotope ratios. But as long as you measure isotope ratios, the same reference materials actually could be used because carbon is present in them. So the purity is the same regardless of whether you're using carbon or hydrogen. But you would have to maybe also certify the isotope ratios, the site-specific isotope ratios. Or at least measure them, which is what we did. But then your uncertainties are really much higher because of the isotope ratio measurements.
Okay. Thank you. Thank you very much. If there are no other questions, please join me thanking Bruno again and congratulating the InMetro team for this award. And I am handing it over to Felipe to introduce the second winning paper. Thank you.
Well, thank you, Zoltan. We are pleased to present the second CITAC awarded paper that will be presented by Giancarlo D'Agostino from INRI. In this paper, the team group proposed the development and application of CY traceable methods for technology critical elements in electronic waste. So thank you very much, Giancarlo, for your presentation, and the floor is yours.
Thank you, Felipe. I will share my screen. Can you see it? Is it fine?
Yeah. Now it's okay. Thank you, Giancarlo.
Let me look for. Okay. So, good morning to everybody. First of all, I would like to thank the nomination of our paper for the CITAC Base Paper Award, also on behalf of my co-author. It's an honor for me to give this lecture. Our paper was published in Journal of Analytical Atomic Spectrometry and concerned the development and application of reference and routine analytical methods providing SI traceable results for the determination of technology critical elements in PCB from electronic waste. The activity was carried out within a research project that was founded by Empire, entitled Metrology for the Recycling of Technology Critical Elements to Support Europe's Circular Economy Agenda. And the paper that we are discussing is one of the deliverables. Let's look to the needs that require the work to be carried out. In particular, the needs were the amount and the environmental impact of high-tech equipments that is having overall in the world. Here you see some figures from the Global E-Waste Monitor 2024. In particular, we produced globally in 2022 62 billion kilograms of e-waste, which is a huge amount of material. And unfortunately, only 22.3% was properly collected and recycled. And this amount is expected to grow up to 82 billions of kilograms in 2030. But I think that these just numbers, they don't give us the idea what is going on. I found on the web this picture, this image that I find dramatic, that shows us the fate of major of the equipments that you are using every day. So the recycling is compulsory for every countries. And unfortunately, we know that recycling has a cost, and we have to look for some solution for compensating a little bit the cost. Luckily, this kind of waste has a value, and in particular, the intrinsic value depends on the amount of the so-called technology critical elements that are inside. Here, the table shows us the list of TCEs that was at the moment of the project. This list is continuously updated for these kind of elements. In particular, we have rare earths elements, platinum group elements, and additional assorted elements. Why they are technology? Because they are needed to produce components for high-tech, for innovation technologies that you see it is the future of our life, and also not the future, but also our current life. And why they are critical? Because they are subjected to a risk of shortage. You see here a map that shows us where these materials are extracted from the land. You can see that Europe doesn't have extractions for these materials. So it is required for us, for Europe, to become a little bit less dependent from abroad. Also in the geopolitical situation that is becoming not so easy. Well, to establish the economic value of these materials, but not only, also to set up the best recycling strategy, is required to quantify these amounts to understand what they are, and then to quantify these elements in the e-waste. So in this case, elemental analysis plays a key role. Unfortunately, at the moment, we don't have harmonized analytical methods available. And moreover, we don't have matrix certified reference materials to validate the developed methods or to establish a site traceability of the results. The only material that is available is the BAM M505A electronic scrap, but this material was produced using pyrite. So the final matrix is not exactly matching the reality. So the first goal of our activity was to develop and apply reference analytical methods based on ICP-MS standard addition calibrations and neutral activation analysis K0 and relative calibrations that will be suitable to certify e-waste matrix reference materials. At the end of the project, we came up also with the development application of analytical methods based on ICP-MS external calibration that are a little bit less time-consuming and less expensive, like standard addition, and can be used in routine analysis of e-waste. The material that we used was taken from the industrial sorting chain. So the e-waste was taken, and then we manually extracted the PCB from there. And then we mechanically processed the material with a cutting mill to obtain a material with a particle size at about 2 millimeters. Then we proceeded with the machining of this material with a planetary ball mill to obtain at the end a powder material that was made from PCB, of course, and with a particle size below 200 micrometers that we believe it's enough for the homogeneity of the material. There were 10 participating laboratories from well-experienced laboratories from NMIs, research centers, and universities. As you can see here in the table, 8 of them developed ICP-MS techniques, some of them with external calibrations, other with standard additions, and one of them both standard addition and external standard calibration. We also had 2 additional laboratories carrying out neutron activation analysis techniques and using the K0 and relative calibrations. As I told before, external standard calibration can be useful and suitable for routine analysis because it is easier. And instead, standard addition and K0 and relative from neutron activation analysis are suitable for certification of reference materials. For what concerns ICP-MS methods, sample preparation was really challenging. My colleagues during the project period reported a lot of issues because this material is made from, it's first of all very heterogeneous and made from plastics and metals. So it was not so easy to reach the complete digestion of the sample before the mass spectrometric measurements. This table shows us the results of the activity that, again, these laboratories spend almost all the time for the development of the digestion methods. You see there are different acid mixtures, different acid ratios, temperature, with or without pre-Ashen step. The first 3 laboratories used a nitric acid and hydrochloric acid mixture with the same acid ratio but different temperatures, with or without pre-Ashen step. There are 2 laboratories that decided to develop a method using alkali fusion, but with different sample-to-flux ratio. Both of them used a pre-Ashen step. Laboratory 3 and Laboratory 5 added tetrafluoroboric acid to the mixture and developed different acid ratios and different temperatures with and without pre-Ashen step. Laboratory 6 developed a complex procedure made from 2 steps and also adding other hydrogen peroxide to the mixture. And they did a pre-Ashen step. Finally, there were 2 laboratories that also adopted hydrofluoric acid to the mixture. So it was a very huge work during the project to develop this procedure that finally succeeded to digest the sample. For what concerns neutron activation analysis, sample preparation is to some extent trivial if we omit that we need to irradiate the samples in a neutron reactor before the gamma spectrometric measurements. Nevertheless, to prepare the sample, we just prepare tablets from the powder material, or we put directly the powder material in the radiation vial. Here is a picture with an example of standards and samples that were inside. This is the tablet that I was mentioning inside, and this is the tablets inside the radiation vials. Of course, let me spend one word for neutral activation analysis. You know, it's a expensive technique. Nevertheless, in this case, became competitive with the ICP-MS methods because the digestion of the sample is not required because it is a solid technique. Now I will show you a number of graphs for the results we obtained and provided by the laboratories. In the graph, you see in the left side the mass fraction value in microgram per gram in this case, and to the right y-axis the difference, the percentage difference with respect to the reference value. You will see gray dots, and the gray dots correspond to data provided with the reference methods, whereas black dots are data provided with, let's call them routine methods with external calibration. Then you will see the error bars. Error bars represent the expanded uncertainty of the results that was provided by the laboratory. And the horizontal dotted line is the reference value that we calculated starting from the reference data. And it was actually a weighted average of the results. So, and we used the uncertainties as weights. There are also, you will see horizontal red bands that shows you in a glance the reference value plus minus its expanded uncertainty. And then also an extension of this band up to, you see here to the right axis, it represents the reference value plus minus 20% of it that we considered as the acceptance zone for a routing datum. Let's have a look close to the results. This is graphs concerning elements that were quantified within the mass fraction range from 0.1 microgram per gram to 10 microgram per gram. For what concerns platinum, you see we had one reference value and then 4 routine values. Only one of them from laboratory 3 was outside the acceptance zone. For what concerns dysprosium, we had 2 reference values from laboratory 10 and laboratory 7. Unfortunately, there was no a perfect agreement between them, so some work should be done on this element. Nevertheless, we had 1, 2, 3 values from routine methods that are in agreement with reference, and laboratory 3 provided a value outside the acceptance zone. Let's move to gadolinium. For gadolinium, we didn't have reference values, so we decided to calculate an equivalent reference using the routine data and always by weighing the results with the uncertainties. You see there are laboratory 5, 2, and 8, which are in quite good agreement. Laboratory 3 is outside the acceptance zone. Let's move to samarium. Samarium, we had 2 reference values, which are in quite good agreement, and laboratory 2 with the routine datum is at the limit of the acceptance zone. Now let's move to a mass fraction range between 10 and 100 microgram per gram. You see, the first is gallium. We had 1 reference value, and the remaining data from routine methods are in quite good agreement and within the acceptance zone. For praseodymium, we had 2 reference values which were in very good agreement, and 4 values from routine data which are within the acceptance zone, and laboratory 3 outside this zone. For palladium, we had just one reference value and then 6 values from routing methods that were very within the acceptance zone. For what concerns gold, we had 4 values which were in very good agreement from reference methods, and then 4 values from routine methods that were good, and laboratory 3 is still outside the acceptance zone. Let's move to the upper mass fraction range between 10 and 1000 microgram per gram. So the amount of elements, it starts to become interesting for the recycling in this case. Let's start with lanthanum. Lanthanum, we had 5 values from reference methods. Unfortunately, one of them is not in full agreement with the reference date, with the reference. And then we had 1, 2, 3, 4, 5 values from routine analysis that are good inside the acceptance zone. Let's go to the lithium. For lithium, we had 2 values from the reference methods that are good, in good agreement, and then 1, 2, 3 values that were quite good inside the acceptance zone for the routing, and laboratory 3, which is, let's say, at the limit of the acceptance zone. For neodymium, we had just 1 value for the reference, and then laboratory 3 is outside the acceptance zone. Nevertheless, we had 4 values that were within the acceptance zone. For tantalum, we had 2 reference values which are in agreement, and again 4 values from routine methods that were good. This is the last mass fraction range that we will observe. First of all, let's have a look to silver, which is an important element to be recycled because it gives a lot of value to this material. And you see that we had 2 values from reference methods that were in agreement, and the laboratory 3, which is in this time was in perfect agreement with the reference and within, of course, the acceptance zone. For cobalt, we had a very nice agreement among the 4 data from reference methods, and then also routing analysis were very good with 5 values within the acceptance zone. For nickel, we had this. For nickel, the situation is similar to gadolinium because we didn't have reference values. Nevertheless, the alternative reference was fine and in agreement. So in the opposite way, the values were in agreement with the equivalent reference. Let's move to the last one, which is copper. I would like to spot out that for copper is 0.1 gram per gram. It means 10% of the material was made from copper, and this makes this material not so easy to measure. And we had 2 values from reference methods that were in agreement, and 3 values from routine data. Only the laboratory 2 was at the limit of the acceptance zone. Okay, now let's have a look to the complete overview. We quantified 16 TCEs, at least by 2 laboratories. 14 of them were measured both with reference and routine, so we can compare routine measurements with the reference. And 2 of them, it means nickel and gadolinium, only with routine results. We also measured 3 additional TCEs, in particular titanium, germanium, and indium, but in this case, they were quantified only by 1 laboratory, so it is unuseful to plot the result. It is difficult to evaluate the quality of these results. In summary, let's go to the summary. We developed 3 ICP-MS reference methods adopting standard addition calibrations, and 2 neutron activation analysis reference methods adopting K0 and relative calibrations that were independently developed and applied by 5 laboratories. Then we had also 6 laboratories that independently developed 6 additional ICP MS methods based on external calibrations. At the end, we quantified 19 TCEs in this PCB material in the range between fractions of microgram per gram for platinum and the huge amount of copper up to 0.1 gram per gram. So reference methods produce data in full agreement for silver, gold, cobalt, copper, lanthanum, lithium, praseodymium, samarium, and tantalum. And the relative expanded uncertainty were fine because they ranged between 0.18% for lanthanum and 7.2% for silver. Some disagreement was observed for dysprosium and lanthanum. All but one routine methods produce data in agreement with the reference value or within plus minus 20% of it. So let's go to the conclusions. The developed ICP, MS standardization, and neutron activation K-zero relative methods are promised for the certification of matrix reference materials made from end-of-life PCB, sorry. Actually, we are participating to international comparisons to test the results, and also we are trying to characterize materials made from PCB and lithium battery and also lead. Soon we will have the results. But also analytical methods used in the industries and research laboratories that are working in e-waste recycling can be harmonized starting from the developed ICP, MS external calibration methods. This is because the performances that were achieved are suited to the purpose of determining the economic value of PCB through TC quantification. That's the end, and thank you very much for your attention.
Well, thank you very much, Giancarlo. And do we have questions for our discussion?
Can I ask something?
Please,
Sure.
please, Ricardo.
Thank you very much, Giancarlo, for your excellent presentation. And let me also congratulate you for the award. I would like to ask you something about the target uncertainty. So you use 20% there. I would like to ask you why, and also associated with this question, why do you decide to set the same target value regardless of the mass fraction? So for low mass fraction and for high mass fractions, you also kept 20%. And if I'm allowed, probably a third question. So this 20% is for the routine analysis, yeah? So what would be for the reference value for a certified reference material? What would be the target there? Sorry for so many questions.
No. Thank you. You touched the critical point of all the work, because actually I should say that it was a real difficult analysis, because the sample digestion was really difficult. Actually, if you observe the result of the digestion, it's difficult to obtain a perfect clean solution. Only two of them of the procedure were achieved at this level, and they were not sure about the complete digestion. So the digestion part is difficult. And we discussed a lot, and we decided to propose this plus minus 20% as a first attempt target, because it is believed that from nothing to have up to have something that you are sure to be within 20% is already a goal. Because again, there is this difficulty for the sample digestion. And this, I should say that the results that I showed you are just work carried out completely independently. So at the end of the day, we came up with these results. Now we can go on a little bit and try to decrease the uncertainties. And it was just the development of and application of the methods. As you can see, we try to compare the results, but it is not an official comparison that is going on right now. I don't know if I explained to you.
Yes,
Yes.
thank you. This is a difficult decision, yes, to take a decision on target uncertainty.
Yeah, I should say that within the consortium, there was also some industrial partners that suggested that 20% uncertainty can be enough.
Okay.
But I understand it is a huge, but still good because the matrix is really difficult.
Okay. Yes, I don't know if you are aware that there is a Eurochem CITAC guide on setting target uncertainty that try to suggest some options, but it is also always difficult, even with a guide or with some help from papers. Okay, thank you.
Thank you very much, Ricardo.
Thank you, Ricardo, for the question. Thank you, Giancarlo. Do we have more questions?
If you
No,
don't
no.
have, I can have another one. So the heterogeneity was a big issue also, yes, a big difficulty, yes. A big difficulty. So your work is for the analytical stage, yes, of course. But did you also discuss the sampling issue somewhere? That can be demanding also.
Yes, there is a guide for sampling issues that is also this is very difficult because when you have a big batch of material, you cannot process all the material together. So there was some attempts to try which is the best way to sample the material and taking a small batch. As this is also a answer to the let's say to the previous question, because it is difficult due to the heterogeneity also of this big batch of material to go below 20% of the representative result. So I personally observed you have in front of you a lot of PCBs, and you ask to yourself, oh, how can we calculate? How can we sample them? The easy way is to do online measurement using XRF portable XRF measurements, and you have to go. You have to machine them a little bit sample by sample and do fast analysis with these XRF measurements. So in that way, you can understand a little bit more what is your distribution of elements. It's a quite challenging task.
Yes, thank you very much. Yes.
You're welcome.
Well, thank you again, Giancarlo, and thank you for your nice presentation and congratulations for the award. And I guess we can go ahead, and I will ask for Ricardo to present the last paper. Thank you, Ricardo.
Okay. Thank you very much, Philippe. So now I will have the chance to listen to the presentation from the third paper. Like I said, there is no hierarchy, but it is the third in the list. This time we have the video because unfortunately the authors were not able to join the meeting. So the name of the winner or the designation of the paper is Navigation, the Complexity, Managing Multivariate Errors and Uncertainties in Spectroscopic Data Modeling. The authors, and I will ask Giovanni to help me, Barbara Giussani, Gilia Gorla, Joaquim Ezenaro, Jordi Rio, Ricardo Bouquet, and this is a very interesting contribution to methodology because it presents a review that underscores the necessity for the scientific community to integrate error analysis and uncertainty estimation into multivariate analysis methods. So we are all using multivariate methods, but like we all know, we have to take care their uncertainty. Okay. Unfortunately, we don't have Barbara online to answer to your questions, but you have the chance to send an email and to ask your questions. So this video, specific video, will not be online on our YouTube channel. It was a request from the authors, but she will answer to your emails for sure if you have any questions. Let me say, sorry for my mistakes during the presentation. There were several and all correlated with myself. Okay, thank you very much. So Zoltan.
So please join me again thanking Ricardo for organizing this excellent session. Congratulations, Ricardo, putting together this symposium, and please join me also congratulating the three winning papers. And with that, I would like to close the 2024 CITAC Best Paper Award Symposium. Thank you very much and hope to see you soon. Goodbye.